start. But let's start here. So a lot of times you'll get your double integral set up like this, where they have the double integral over some domain D, and then they describe D. And most of the time they'll describe it, and it's up to you to try to draw it out and try to figure out how it's going to look like in a two-dimensional plane. And once you get that drawn out, then you would figure out whether you should take the integral with respect to x first or y first, depending on the graph. And so let's start it. D is enclosed by x equals 0 and x is equal to this. So you have to know what these graphs look like. I know that the second one is x is a function of y, so if you just kind of put things together, you should see that it's kind of like a circle. Can you get a circle out of that? Square both sides, you get x squared plus y squared is equal to 4, so a circle of radius 2. And it's on the positive side of x, so this would be the semicircle on the right side. Okay? So I have x is equal to 0. That graph is pretty easy. That's the y-axis. And then I have the graph of x is equal to this thing, which is, like I said, the positive side of x of the semicircle. And your region is that region over here. And if I were to draw a line parallel to the y-axis, saying if I want to try to integrate with respect to y first, I can do it, except now I would be going in and out of my region at some other things with y's. So this is more complicated. So integrating with y first with respect to y first is too difficult. It's not impossible, you can do it, but it's too difficult, so what we'll do this way, we'll do it with respect to x first. So with respect to x first, you would set up your x limits, and then you know that your y limits are going to be constants. Then you would draw a line parallel to the x-axis. And regardless of where you draw that line parallel to the x-axis, you're always going to be entering the region in the same function, and that's a function x is equal to 0. Say it again. WRT is with respect to x. So we're going to integrate with respect to x first and draw a line parallel to the x-axis. We're going to enter through the region when x is equal to 0, and then we're going to exit through the region when x is equal to that thing. Right? So a couple of key things to watch out for. If you are integrating with respect to a variable, you want to make sure that that variable doesn't occur in the functions, because that would be a function defining itself. For you computer people, we don't want to do recursive stuff here. So if you have a function of x, or you have x as a function of something, x has to be a function of a variable that's not x. So x is a function of y in this case. And then, like I said, the y limits, the outer limits have to be constants. And so you just look at y values, where you're going from. So y goes from -2 to positive 2. Those are the constants. Yes? Because this is a circle, a radius 2. If we square both sides and bring the other side over, and then you look at 4 as the root. Yeah, you could also plug 0 in for y, and then your y or 0 for x, I guess.
0 for x, I'm sorry.
And then you'll get your y-intercepts. Okay, so then here's our integral. We have our integrand as 3xy squared. We're integrating with respect to x first. So our dx, x limits are going to go from 0 to square root of 4 minus y squared. And then our y limits are going to go from negative 2 to 2. And most of these in the homework will have you set up an integral where it actually is manageable. You don't need anything fancier than u substitution. And if you have to use anything fancier than u substitution, you should probably take a look at it again and make sure you're doing it correctly. Because most of them is just going to be a simple u sub. Like this one should be a simple u sub after you do this integral with respect to x. You'll have x squared, right? And then when you put this in for x squared, it'll take away the square roots, and then you would just distribute. I'm not going to do it. You should do it for practice. I already know how to integrate, so you know how to integrate. You just need practice doing it, so I'll let you finish this. All right. Etc. Let's go to another problem. How'd you guys feel about that triangular region? 1. Actually, after class yesterday, I decided to make a short video of it. So I have a solution on a video and a PDF. So I'll post that up in Canvas. So let's do something else. Let's try number 17. So under a plane and above the region bounded by something that's described in x and y. So what you should think about when you're reading this is, first of all, don't panic. So the thing to identify is what parts of the graph describe the 3D function, so that's what you're going to put in the integrand, and what part of the description describes your two-dimensional domain that you're integrating over. And if you can do that, then you're, I was going to say you're halfway, but you're not close to halfway yet. But you're steps now towards actually solving for this. So what you want to do for the 3D function, if it's not already obviously solved for z, then you would just solve for z. And then you have z is equal to f of x, y. Now you would have a function of just x and y. And then, hopefully it'll also be clear that this is your domain. That's the d that you're going to be integrating over. So this domain is what you're going to draw in 2 dimensions. Okay? So if we figure these things out, we have z is equal to 9 minus x plus 2y. That's your integrand. That's what's going to go inside of the double integral. And then figuring out what your domain is will help us figure out what our limits are. And this is where you're going to need to be able to look at these two-dimensional relationships between x and y and go way back to pre-calculus and be able to graph these things. If it's lines, try to draw it as y equals mx plus b and see if you could do it that way. This is some sort of parabola that has some sort of a shift or whatever, so you need to be able to think and do this quickly. And I was talking to somebody about test situations. When it's a test, you have to not only know how to do the problems, but you have to be able to do it quickly. And this is one of those things that if you're a little rusty with your graphs, then doing a bunch of these problems will help you, work through some of these things. Like this, x plus y is equal to 1 is a line. You have to know that that's a line because the x and the y are not being squared, square rooted, or put into some weird functions like sines or ln's. So if I write y equals negative x plus 1, I know I have slope negative 1 and a y-intercept of positive 1. Yeah? You could do that as well. Yeah, so graphing calculators, if you feel comfortable, if you have a good command of your graphing calculator, that's fine. We have y is equal to minus x squared plus 1 for this one. So I know that this is a parabola, a regular parabola that has been turned upside down and that's been shifted 1 unit. Okay, so these are the things that as Calc 3 students you have to try to be quick on. So what did I say? This is a negative slope at 1. That's the first graph. So this is my x plus y equals 1. And then upside down, y-intercept at 1. And then between these two pictures, I can kind of see where the region is, right? So the region is a small bit of region over here. All right, so it looks like in this particular scenario, you could do either with respect to x or with respect to y. Can you see how? So either with respect to, let's say with respect to y first, draw a line parallel to the y-axis and then figure out what you're going to go into and get out of. So with respect to y first, you have your y limits going first and then your x limits going second. And your outer limits are always constant, right? So now the graph here, the line is x plus y is equal to 1. So I want y by itself. Y equals negative 1 or negative x plus 1. That would be my first function. And then you're going to be in the region until you get out of this, so you need to solve for y here. Y is equal to 1 minus x squared. That would be my top function. Okay? So let me rewrite this as 1 minus x instead of negative x plus 1. 1 minus x squared. And our x limits are constant. They go from what to what? Go from 0 to, they intersect here. I'm assuming they intersect at 1. Okay. Now let's take a look at the other scenario. If we decided that we wanted to integrate with respect to x first, let's see how easy that would turn out. If we do this with respect to x first, we would draw a line parallel to the x-axis. And then what I'm going to notice is that I'm going to enter through the same line, right? But I need to now express that line as x as a function of y. So x equals 1 minus y. So that's a good lower function to have. And now my parabola, which is written as x squared plus y is equal to 1, I have to solve for x. So now this is where I would probably want to stop and say, I got to do a square root. So because I have to do a square root, the other one's already done. I'd rather stop here. But let me keep going here. You would bring the y over to the other side, and you would take the square root. Now when you take the square root, there's a plus and minus. So you have to decide on which one it is. Is it the plus or the minus? It's the plus because this is where x is positive, right? So you got 1 minus y, which is a slightly more complicated limit to mess around with. It looks like the y is going to go from 0 to 1 also. But this is a good example where we can see this region being described in two different ways, and one of them is clearly easier than the other. Easier to integrate. If you can somehow stay away from square roots, that would be great. And so let's set up the double integral for this setup. We're going to integrate with respect to y first. What was the function, by the way? Oh, the function is this, right? That plane. So 9 minus x plus 2y. And then we're integrating with respect to y first. And the y limits go from 1 minus x to 1 plus or 1 minus x squared. Oops, this is dy, not just y. And then our x dx is going to go from 0 to 1. So that's our integral. That's the integral you plug it into Wolfram alpha. It's definitely computable, right? I mean, this is with respect to y, it'll square it, then you just have to put in those functions, and then you'll still have a polynomial with respect to x, integrate from 0 to 1. It's still manageable. And had we had a square root in there, we might have had to do a square root something where we might have to do some special substitution or some trig substitution or something. Who knows? Okay. Any questions? All right, let's take a look at a couple more. So number 18 is similar to that triangle one, which will kind of force us to come up with equations of lines. But let's see how this is going to work out. Let's do number 18. Find the volume. So you have a surface in 3 dimensions, and then the triangle with vertices, whatever. Are these the same vertices that we had last time? slightly different. Oh, this might be easier. I don't know. Let's see. So anyways, you figure out your integrand. Your z is already solved for. This is your 3D surface. And your 3D surface is what's going to go inside of the integral. And this is your domain. You're going to integrate over this domain, this two-dimensional domain. So I think the only thing we need to worry about is this two-dimensional domain. So we got 1, 1, 4, 1, and 1, 2. Yeah, this is easier. It's easier because it looks like a right triangle, and whether you integrate with respect to x or y first, I don't think it'll matter. The other problem that we had, it didn't matter what we integrate with respect to, because with respect to one way, it looked like it would be, we would need two integrals. So in this case, we have a choice. We can integrate with respect to x first or y first. But first, we need to figure out what these lines are. The horizontal and vertical lines are usually x or y equals to something, right? So we got a horizontal line, y is equal to 1. We got another horizontal line over here, x is equal to 1. And now we have another line over here that looks like it might be so we could do the rise over run. So any way you want or any way you can, find the equation of the line. So we got 2 points. We need a slope and a point to figure out what that line is. So what's a slope? Negative 1/3. So you got y minus y1. I'm going to pick this point. So y minus y1 is equal to the slope x minus x1. So this is how I'd like to do my equation of the line. Some people use y equals mx plus b and then they solve for b. That's fine, whatever, however you want to do your line. I'm going to write it like this and then decide whether or not I'm going to do with respect to x or with respect to y. Actually, you guys decide. What do you want to do with respect to x or with respect to y first? And it doesn't matter. I'm looking at the function that we're integrating, and I'm looking at this region and the lines. It doesn't matter what to integrate with respect to. So pick one. What? X. Let's do integrate with respect to x first. So that means I want my x limits figured out first, which means the line that I would draw a line parallel to the x-axis, and I would figure out that I'm going to enter through the region at x equals 1. And I'll be inside of the region. I'll be going out of this region when x is equal to, now I need to solve for x here, right? So that would be negative 3y plus 6 equals x minus 1, and then add 1, so that's 5. Is that correct? 7? Is that good now? So I'll write x is equal to 7 minus 3y. And then y goes from where to where? Constants, right? And then here we already have our y limits in our y-axis, so that's 1 to 2. Okay? So just to remind us of what we're doing, we're going to let y be equal to 1, and then you're going to go from 1 to 4. If you let y equal to be slightly bigger than 1, we're going to go from 1 to whatever this function is. So you're making your cuts this way. If you think back at the sliced bread analogy, these are the slices that we're doing. And then your surface is somewhere out of the screen here in the third dimension. And then you're making your slices this way. All right, I think that looks good. We can set up our integral. We have our function z is equal to 3 times xy. And then our dx, our x limits are from 1 to 7 minus 3y. And then our y limits, dy, is going from 1 to 2. Again, you're dealing with polynomials, no big issues here. Okay. Does it seem okay now? Compared to yesterday? Maybe I just threw you guys to the wolves? Huh? Paraboloid bounded by planes. All right, let's do number 22. Let's start getting fancy here. So this, at some point, you're gonna, like I said, you're gonna start to need to visualize things in 3 dimensions, and a good chunk of that would be getting a good handle on the quadric sections or quadric surfaces. So you got to know what a cylinder looks like, a hyperboloid, a paraboloid, ellipsoid, all those things. So remember when they say cylinders, right? It's not necessarily just those round cylinder-like cans. It could be a parabola that's been swept along like a trough, for example. Ooh, this one's going to be hard. Can we not draw it?
Can we use the 3D grapher then?
Oh, we can, but even the 3D grapher, I'll show you how it looked like in the 3D grapher. Unless you have like really good control over 3D graphing, you'll just see a bunch of surfaces that look like they're merged together, and you have to look very carefully to try to figure out what the actual solid is. And that itself is an exercise for you guys, maybe some extra credit or something, if you want to mess around with doing that. But it might require parametric surfaces, trying to do parametric surfaces, which we'll eventually have to do. All right, z is equal to 0. I know what that is. That's the plane, xy plane. All right, let's see if we could draw this. I'm trying to see if I can look at these equations without drawing it, but I think this gives us a good indication of what's happening. We have the surface, the solid, from the floor, and then this will be your top level. So I'm kind of seeing between these two that this is going to be my integrand. This is what's going to go inside of the double integral. And so now I'm kind of looking at this and this as describing what's happening in 2D. So we may have just gotten away from drawing this in 3 dimensions. What? Z is equal to 12? Well, that might be the highest point of this, yeah. All right, let's see. Y is equal to x squared. Let's draw this in 2 dimensions. Y is equal to x squared, and y is equal to 4. So it looks like we're interested in this region, and it seems pretty clear what to integrate with respect to first, right? Does it seem clear? What do we want to integrate with respect to first? Y, right? Y? ¿Por qué? So if you integrate with respect to x2 first, you're going to go in and out of the same thing where you need to solve for x is equal to positive and negative square root of y, and that will end up being your 2 functions and square roots and stuff. So let's undo that. And if you were to integrate with respect to y first, you would draw a line parallel to the y-axis, and it seems pretty clear your entry point and your exit point of the region. So with respect to y first. And so you set up your y limits, and you know that your x limits are going to be constants. So y goes into what function first? Yeah? Yeah, we want to draw our axis just for my sake at least. I draw my axis as the x going horizontal, y is vertical. And when I say draw that line, the order, the direction in which it goes from negative to positive, right? And so that when I say which one it goes into first and out of second, I'm assuming this line is going from negative to positive. Okay, and that goes from. If we're drawing with respect to x first also, that goes from negative to positive also. All right, so what's my lower function? And my upper function? Okay. And now my x limits are constants from what to what? I guess we need to figure out where they intersect, right? And most of you already know that goes from negative 2 to 2. I think that's it. We have our integrand, and we have our limits. Our integrand is 3x squared, right? And we're integrating with respect to y first. So that's just dy. Y goes from x squared to 4. And then our x, dx, is going to go from negative 2 to positive 2. All right, just for fun, let's take a look at this. And let's see if we can identify where our surface is. Maybe if we can make these slightly transparent. Any other adjustments we need to make to try to see this? Maybe the bounds. All right, we want our y. Our y went all the way to 4, right? So we want to probably go at least to 4. So I'm going to set this from 0 to 4. oops, this is 0 to 4. My purple graph didn't go all the way.
Maybe you should just do like one by one by one. The shape will be the same.
One by one by one? All right, so I guess it's kind of difficult to try to imagine how these things would look like if we just randomly draw those surfaces. So somewhere in here there's a solid that's being described, and maybe I'll see if I can refine it and make it. What should be 12? So I think there's too many things going on here. So anyways, like I said, this requires a little bit more refinement. So maybe while you guys are working on the worksheet, I can mess around with this and see if I can come up with a... Would you throw them away?
I'm pretty sure it's at home like that.
Okay, well, I have a couple more copies.
Region of type 1 and region of type 2 mean?
Region of type 1 means you integrate with respect to y first, and then with respect to x. So I don't like the idea of calling it region of type 1, type 2, because I think it's just the order of integration.
Yeah, I think that's confusing.
All right, if you guys don't have a worksheet, I have a few more copies here. You guys can come up and get it. We left off on number 4, I think. So 5, 6, 7, 8 would be great. And then in the last 5 minutes, I'm going to do one problem from number 10.
But is this something scattered by the coordinate plane, or is it just x, y, z?
The x equals 0, the z is equal to 0, y is equal to 0, and yeah. It's up to you.
I was going to say, like,
Number 7 we did yesterday too.
7?
Yeah.
I just think
Okay, so all right, try to actually do 6 and 7, and then if you want, I'll show you the answers. So in the last 5 minutes, I want to do another example, and some of these are generally well, I don't know. That's the word I was going to use, but actually, I don't want to do that one. Let's start off with something kind of simpler in the same idea. Now let's take a look at this integral and start off by trying to integrate it. And if you look at this integral and you try to integrate it, the first thing you have to do is to try to integrate this integrand with respect to y. So just imagine integral of 3e to the y over x with respect to, oops. So trying to integrate this is how should we say it? Impossible.
Why?
Because x is a constant, right? So if x is a constant, we just ignore that, pretend it's 5 or pretend it's 1, and we're really integrating this, e to the 1 over y. And if you look at any integral book, there's no antiderivative for this. So, because there isn't. You can find estimates for this, but we're not going to be able to take the integral of this thing. You can. Because we're not done with the problem yet. So the idea is that there's a bunch of functions that don't have any nice closed form integrals. And so Mathematica comes up with these names of functions. So this is called it's a special letter E. It's called the exponential integral. I don't know what that means. But it's one of those things where there's no, quote, closed form function for this antiderivative. And the most famous one is the integral of e to the x squared. We know that we can't integrate that. I hope you know that you can't integrate that. So there's a handful of functions, actually there's more than a handful. There's a handful of functions that we can actually integrate. And there's a million more functions that we cannot. And so that's why I made a comment one time about coming up with examples. In Calc 1, I can come up with any examples and take derivatives of any function. In Calc 2, I have to be really careful about coming up with examples of integrals because you can't integrate everything. So this is one of those things you can't integrate. Now, turns out that if we switch the order of integration, then we would be integrating with respect to x first. And that is manageable. Because y would be a constant, I just like x over 3. I can integrate e to the x over 3. So our task is to switch the order of integration. And to do that, you would need to draw this. So what you do is you translate from integral to a graph. Well, let's see. Let's switch the integrals. X over 3, 0 over 3. 3e to the x over y dx dy. What's the problem? Outer limits are not constants. Okay? So we can't just switch the dy dx and switch the order of integration. What? You have to, yeah, resolve it. Yeah. Right. So what you need to do is you need to write the limits out. So y limits go from x to 3. Do you see that? And x limits go from 0 to 3. So then you would graph it. Goes from x. Y goes from x to 3. Y is equal to x. Y is equal to 3. Right? And x goes from 0 to 3. So this is the region. Now I don't want to go with respect to y first. I want to go with respect to x first. I would enter x through what? X equals 0, and exit x through x equals y. And then the new outer limits will be constants. Y goes from 0 to 3. So now your double integral is going to be first with respect to x from 0 to y, and then with respect to y from 0 to 3. And now you can at least integrate this. You do a simple u substitution, y is a constant. You can take that out, right? And then after you do that, you integrate with respect to y. So the last 3 problems in number 10 are going to be these cases where you cannot integrate the way it looks like now. You have to redraw the region and rewrite your double integral, and then you should be able to solve for it.
Would it fairly obvious you're asking the first one, I guess, because it's or might just throw in a test and we're like, oh, this doesn't make sense.
Yeah, I'll probably won't tell you to reverse it, and you should know to reverse it.
Okay.
Okay?